Hello, welcome back to today's class. Today we will discuss about mesh analysis of circuits which contain current sources. In mesh analysis, if we have current sources, we run into problems because it is not possible to express the voltage across a current source in terms of its current because we cannot apply Ohm's law to a current source. For this reason, mesh equation cannot be written for a mesh which contains a current source. And consequently, we need to treat current sources in mesh analysis as special cases, just as we treated voltage sources as special cases in nodal analysis. In mesh analysis, from the previous class, we have already learned that there are two types of branches. In the first type, the branch belongs to only one mesh, so the magnitude of the branch current and the mesh current are equal. In the second type, the branch current is equal to the difference of the two adjacent mesh currents. Using these principles, we can identify two cases for current source in mesh analysis. If the current source belongs to a branch of type 1, then it is case 1. If the current source belongs to a branch of type 2, this is an example of case 2. So these are the two cases. In case 1, the current source is in a branch which belongs to only one mesh. In this case, magnitude of mesh current and branch current are equal. The branch current is equal to the value of the current source. So mesh current magnitude is equal to the value of the current source. In case 2, the branch current is again equal to the value of the current source, and that branch current is equal to the difference of the two adjacent mesh currents. So the difference of the adjacent mesh currents is equal to the value of the current source. Let's look at case 1 first. In this circuit, we have a 16 ampere current source which belongs to only one mesh. There are two meshes in this circuit and we have assigned I1 and I2 currents, and 16 ampere is in a mesh where the current is I2. In mesh 1, there is no current source. We have 3 resistors and 1 voltage source, so we can write the mesh equation in a straightforward manner. For 3 ohms, the voltage is 3I1. For 6 ohms, the voltage is 6I1. For 2 ohms, going downward, the voltage is 2I1 minus I2. 30 volt source is a voltage rise, so this is positive on the right hand side. In mesh 2, we cannot write mesh equation. However, we note that because this is case 1, the magnitude of I2 is equal to 16 ampere. And we have to determine whether this I2 is plus 16 ampere or minus 16 ampere. If the current of the current source and the mesh current are in the same direction, then the value of the current source will be equal to the mesh current. If the mesh current and the branch current are in opposite direction, then the mesh current will be negative of the current source. That is the case here. So we have I2 is equal to minus 16 ampere. So we have two equations and we have two unknowns, I1 and I2. Solving, we get I1 is minus 0.18 ampere. So we can see that like case 1 of nodal analysis, case 1 of current analysis actually made the solution easier. And the case 1 of nodal analysis is similar to case 1 of mesh analysis. If we understand one approach, the other should be straightforward. Now let's consider case 2. In this circuit, we have a 6 ampere current source which is common to two meshes. The mesh currents are I1 and I2. 6 ampere is in a branch common to both meshes, so this is an example of case 2. If we look at mesh 1, there is a current source. If we look at mesh 2, there is again the current source. So we cannot write mesh equation either for mesh 1 or for mesh 2. This is similar to case 2 of nodal analysis, where a voltage source is connected between two non-reference nodes. In that case, we cannot write node equation for either node, and we adopted the supernode principle to write equations. This analysis is also similar. When we cannot write equation for mesh 1 or for mesh 2, we form a super mesh by combining the two meshes. This is how the super mesh looks like, and when we combine the two meshes, we go along the outer perimeter of the circuit. Now, if we look at the super mesh, there are 4 resistors and 2 voltage sources. There is no current source on the super mesh. For this reason, it is possible to write the mesh equation in a straightforward way. For the 4 resistors, the voltages will be 4I1, 9I2, 6I2 and 1I1. There are 2 voltage sources, both are voltage rise, hence they are positive on the right hand side. So this is the equation that we get. By combining two meshes into one super mesh, we have obtained one equation. We now need another equation. To get the second equation, we will look at the current source. This branch is common to two meshes, and this branch current is equal to 6 ampere. This branch current is equal to the difference of the two adjacent mesh currents. The question is 6 ampere equal to I1 minus I2, or is it I2 minus I1? For that, we have to compare the direction of 6 ampere with the mesh currents. In this branch, I1 and 6 ampere are in the same direction. I2 and 6 ampere are in opposite directions. So I1 will be positive and I2 will be negative. We can write I1 minus I2. So we now have two equations for the two unknowns. Solving these, we get I1 is equal to 10 ampere and I2 is equal to 4 ampere. We can summarize how to get two equations from a super mesh that contain two meshes. The first equation we get from applying mesh equation along the super mesh, and the second equation we get by looking at the current source, which is common to two meshes. That's all for today. Thank you.